Going on to topic 3 of chapter 10, we're going to continue with this counting type of thing, but now we're going to use permutations and combinations. And in the sake of repetition, we're going to mention there are some key words that you should note as we think of permutation, and I'm going to say it a number of times, hopefully it will sink in. For permutation, order is important. For combinations, order is not important. So we'll be repeating that throughout, but let's go on to look at the section in some detail. Again, we're going to recall a club. There are 5 members in our club, and we're going to consider this. How many ways can all the club members arrange themselves in front of a photographer for a photograph? And secondly, how many ways can the club elect a president, a secretary, a treasurer, if no one can hold more than one office? Recalling from our last section, we said we could use the counting principle, where there are 5 members, and what are the arrangements? Well, there are 5 different arrangements. So we have 5 factorial, which is 120. Now again, recalling the previous section, we had said that when 3 of these are going to be selected, what possibility? Well, it would be you have 5, then 1 is not included anymore, then it's 4, then it's 3. We get 60. Now, how many arrangements are there of 5 things taken 3 at a time? Well, this is kind of a new way of generally stating something, and we might say the factors begin with 5 and proceed downward, just as the factorial product, but do not go all the way to 1. Here the product stops when there are 3 factors. Just this. Now there is a way that we have where order is important, and counting problems are done this way, and the method is called permutations. Now there is a formula for this. There's a number of different ways to write it. We're going to stick with this way. The number of items in the set, and we're going to use permutations because order is important, and then how many are you going to take at a time? That's what the R stands for. The text goes on to show how the formula will be derived, and we keep in mind that R, the number of things you're doing, has to be less than or equal to the total number of items you're dealing with in a set. That is the N. So we end up with the formula for permutation, and of course you're going to write this in your notes. And again, you are hopefully familiar with parts of the formula. For instance, you know factorial, and you know subtraction, and we know what to do with the factorials in something like this. So we'll have some practice using the formula, and we're going to start with example 1. And to understand the symbolism of it a little, here we have 4 items that we're going to use permutations, and we're going to take 2 at a time. So we want to put that into our formula, and we'll pretty much follow what is here. Now, looking at this first one, we see that there are 4 items. So according to our formula, that'll be 4 factorial. Now we are going to divide that by the total number of items, 4. But now we're going to subtract our R value, which is 2. And that will be factorial. So as we do this, we can go 4 times 3 times 2 factorial, and then subtract this, gives us 2 factorial. So the 2 factorials cancel out here, and we're left with 12. So you get the pattern of how to convert what they give you when you put it in the formula for permutations. So the 8 factorial goes on top, and then 8 minus R in parentheses, factorial. And as you do this calculation, notice we can do it this way. 8 times 7 times 6 times 5 times 4 times 3 factorial, and then this 8 minus 5 is 3 factorial. So these can just cancel out, and it would just be this. Or you could have done the 8 factorial and the 3 factorial, which is 6, and 6 into that would have given you this. But this method gives you this answer directly. So a little something. Let me clear it for the next example. So now we have 5 items, permutation, 5 at a time. So we have on the top 5 factorial. On the bottom we're going to have in parentheses 5 minus 5. Now 5 minus 5 is 0 factorial. But I don't know if you recall, but 1 factorial and 0 factorial both equal 1. So there's our 1. So it's 5 factorial gives you the 120. And they're giving you the general statement here that anytime the number of items available and its permutation and 5 items are going to be selected, it's just equal to 5 factorial. So what they're saying here, if both ends are the same in a permutation, it's just this number, n, factorial. General rule. In example 2, they're featuring that in some of your calculators, they may be able to evaluate permutations directly by putting this into your calculators. And these are the examples, these are the answers. Now in letter C, the number is so large that you won't be able to read those digits, so they usually convert it to scientific notation, where this is the number of decimal places you have to move it over to get the full answer. Now that you are allowed to use your notes, that's rather important. We're looking at problem-solving strategy. Permutations can be used anytime we need to know the number of arrangements of R objects that can be selected from a collection of N objects. This is your full set. This is what you will be selecting out of it. Now here a keyword also is arrangement. An arrangement implies that you are ordering. That order is important. So where we had suggested this earlier as a good term to associate with permutations, order is important. And another key part, repetitions are not allowed. So in your notes somewhere, you need to put these two qualifiers in regard to permutations. One of the key words, arrangement, ordering. Order is important. Repetitions are not allowed. So later in this section, one of the choices you will be making is permutation involved? Or later we're going to see the other word, combinations. So in example C, again, this is the model you're going to follow should you get something like this in your homework. How many non-repeating, so again, repetition is not allowed, this will be a permutation, 3-digit numbers, this is the number of selections when only these digits may be used. And we have 1, 2, 3, 4, 5, 6. So this will be 6 permutations, and we're picking out 3. And that's what we have here. So the formula for this, if you put it in the other way, and I didn't have any place to write it, so I'm overwriting here. So permutations, 6 factorial, and then divided by 6 minus 3 in parentheses, factorial. And we're writing out our first few factors, 6, 5, 4, and then 3 factorial, because our denominator becomes 3 factorial. These cancel out, and that's why they're showing it to you this way. And you might say after a while you can sort of do this step mentally, but I think it might be too early to start off right now. Now in example 4, this takes very careful reading and lots of things going on. So you have an account that's going to consist of 2 letters followed by 4 digits and then 3 more letters. Repetitions of the letters or digits are not allowed within any of the three groups. Now, since repetitions are not allowed, these are going to be permutations. But the last group of letters may contain one or both of those used in the first group. How many such accounts are possible? Well, in part 1, you determine the first set of 2 letters. Now remember, all letters can be used, so there are 26. So this is a permutation because order is important and repetitions are not allowed. So we have 26 permutation, 2 items at a time. We're then going to times that by how many digits are there? 10 symbols. And we're going to take them 4 at a time. But repetitions are not allowed. So this is a permutation. And then finally, in the last, you have again the choice of your 26 letters, taken 3 at a time. So if you did these in parts, you would get this from the first part, times this from the second part, times this from the third part, and you get over 51 billion possibilities. Fundamental counting principles, but using, in this case, permutations. Now, as we go into combinations, we want to see if we can figure out generally what's the difference. Well, in combinations, order is not important. Remember, we said in permutation, order is important. So if we had our same club that had these members, and they were electing a president, and then a secretary and treasurer, order was important. But if they were just going to have committee members, there is no distinction between the committee members. This would just be a grouping of things, and where B, D, and E in this order was significant, reversing them, E, B, D, would be significant if it were permutation, but now they're the same. So order is not critical, and this is what we find in combinations. Now they go through and describe this in detail. I'm not going to read it all to you or go over it in any detail at this time, but to say that there is a formula then that comes out when you are dealing with combinations where order is not critical. And we saw how the formula was derived, again, not a critical thing. The key is this is the formula for combination. So we use part of it as the permutation, part of it as the counting of elements that we're selecting, the factorial, and it gives us this formula. So we see from n combination of r, we'll see that the n, we take the factorial of that n, we're going to take the factorial of that r, but now in the parentheses, we're going to subtract n minus r and that factorial. So we'll want to use this and practice this as we do example 1. And let me set it up for you. So as not to go too far, as we look at our first example, our n is 9 factorial, and then our r is 7 factorial, and then n minus r, 9 minus 7 factorial. This subtracts and gives us 2 factorial. Now, in figuring this out, we can go 9 times 8 times 7 factorial on the top. And then this is going to be 7 factorial there. And then we know that 2 factorial is just 2. Now we know we can cancel this out. 2 will go into there once. 2 will go into there 4 times. We go 9 times 4 is 36. So again, they're showing you if you just had these big numbers, but hopefully what I'm showing you is that there are shortcuts to deal with them. And I think in some calculators you can put this into your calculator and get this answer. And in doing example B, there's our combination, there's our setup. I've written it out this way. So I stopped at 18 factorial. So now I can cancel these out. And notice I can cancel, and I've written 6 factorial out. I left the 1 out because that doesn't mean anything. But I can go, 6 goes into there once, 6 goes into there 4 times, 4 goes into there once, and that eliminates the 24. Now 5 will go into there once, 5 will go into 20 4 times. And 2 goes into there once, 2 goes into there 11 times, and 3 goes into there once, 3 goes into 21 7 times. So you now have then 23 times 11 times 7 times 4 times 19. Still a lot of work, but showing you, again, not so much a shortcut as compared to what we did before. But this is your answer. So that's why you want to be able to put your work into your calculator directly when you're working with combinations. And I should have a link to a YouTube video up here to show you how to use your calculator to input this information. So one of the key things then that we need to include in your notes, as we did for permutations, combinations, when we do summary, again, looking at problem-solving strategy, when we deal with combinations, share an important feature with permutations in that repetitions are not allowed. And they differ from permutations in one key distinction, which is that order is not important with combinations. Combinations are only applied in these situations. Repetitions are not allowed, and order is not important. All right, so we'll be going on to topic or example 7. And another key word here is subsets when we're thinking of combinations. Subsets, because the order, you recall way from the beginning of class, subsets, there is no distinction in order. They're all members of a subset regardless of their order. So these would be combinations. So find the number of different subsets of the size 2 if there are 4 elements in the set, and then list them. So again, this is a subset. The key is combinations. There's our combination setup. We put it in the formula, we get 6. So notice we do not have repetitions here, and all of these are different. As we look through these, again, we're wondering, is order important? If order is not important, then it's a combination. If order is important, it's a permutation. But we're still doing basically here combinations. A common form of poker involves hands or sets of 5 cards each that will be dealt from a standard deck, 52 different cards. How many different 5-card hands are possible? Well, again, order is not important. You're just looking for different hands. So your overall number of items, 52 in a card deck, and it's combinations, and you're going to select 5. So there's the formula filled in, and over 2.5 million possible combinations. Would you ever think that? As we look at example 9, subsets of paintings. So a key word that you're dealing with combination here is a subset. Remember, subsets, the order is not important. She would like to buy 10 different paintings, but she can only afford 4 of them. In how many ways can she make her selection? Well, the total number of items, 10. It's going to be a combination. Order is not important. And she's going to select 4. And we get this. Now, another interesting thing that's going on here is that if you were to switch this around a little, and instead of putting 4 there, you put 6 there, the results are the same. A very interesting observation that if we were doing textbook items, this is where they ask you to prove that that is in fact true. And there is the proof of it. Now, this is some general guidelines that should be included in your notes of which method to use. Is it a permutation you're dealing with, where order is important, arrangement is important, or is it a combination where arrangement's not important, order's not important? And you can read and look this over. And again, the formulas are there. Another thing clue words. I would call them keywords. Arrangement is important. The schedule, the order. For combinations, set, subset, a group, a sampling, a selection. And through experience and observation, hopefully you can pick up on this. And in these, again, as you read them, you will be making a decision whether you're going to use permutation and or combinations, and may also reflect on what we did earlier, the fundamental counting principles. So in all cases, decide carefully whether order is important. Now, once order is important, that will determine whether you're going to use permutation or combinations. So, let's go through some of the problem-solving strategy. Number 1, if selected items can be repeated, use the fundamental counting principle. For instance, how many 4-digit numbers are there? And we did this earlier, where we said of the symbols for the digits, there are 10, but the 0 didn't count in that first position, so we can only have 9. But then in the next 3 positions, there could be all 10 symbols used. So that would be 10 times 10 times 10, which they're summarizing here as 10 to the 3rd. And this is 1,000 times 9 is 9,000. And example 2. In example 2, if items cannot be repeated, order is important. Again, you'll use permutation, and you write it as a permutation. We have 8 people line up for tickets. How many ways can 3 of the 8 be counted? And it would be 8 altogether. Permutation, we're taking 3. So 8 factorial divided by 8 minus 3 factorial give you 336. And then moving on to item 3. If items cannot be repeated, and order is not important, we use combinations. Because since order is not important, we're dealing with sets in a sense, or subsets. How many ways can a committee of 3 be selected from a group of 12 people? And then just plugging that in to your combination formula. And you're showing this in your homework logs. Keeping good records, your notes. All right, let's go on to example 10. We'll give you a moment to read it, and then we'll decide. So, 3 toys, 7 children, and they can be distributed among those 7 children. 3 toys. So this is a fundamental counting principle in which the 7 children can get the 3 toys. The 7 children again can get the 3 toys. The 7 children again can get the 3 toys. So it's 3 7 to the third power, which is this. All right, let's take a look at example 11. So in reading this, it says there 2 members are women and 3 are men. Although the question mentions only that the committee must include exactly 1 woman, to complete the committee, 2 men must also be selected. So in a sense, this is a problem in 2 parts. So in the first part, order is not important. We have 3. Well, let's go over here to our first part, actually. We have 2 women. 1 is to be selected. So there are 2 ways. So once that is done, in a sense, we now have the 3 men, and 2 of them are selected. And that can be done in 3 ways. So once we have the parts, we then can use fundamental counting principles, which is 2 times 3, which gives us 6. And they are showing the possibilities listed as sets. Again, time spent to read the problem, determining what you're going to use. We have counting principles, permutation, combinations. We'll pause. Well, as you read it, you hopefully can think this one's easy. Is order important? No. So we're going to use combination. There are 48 members. We're going to select 10. So we set it up as a combination. We end up with this. And again, putting that in your calculator, you'll get over 6,540,715,896 different ways. Wow. There's only 48 members. Now here we have fraternity, 10 members. We're going to select 4 to escort homecoming queen candidates. Well, here they're stating that order would be important because the different orders will pair the men with different women. So order is important. We use permutation. And there's the formula. Going on to example 14. We'll pause again. Now, as we look through all of these, your textbook and notes are going to be super critical because you will use that as a model, a guide. Here we're going to have 9 basketball players divided into groups of 4, 3, and 2 players. So in a sense, there's 3 different combinations going on here. The first, out of 9, you're going to select 4. Order's not important, this many ways. Then, since 4 is selected, there's going to be 5 remaining. You're going to select 3. There are 10 ways. Then there are 2 remaining. And then out of 2, and we said when this occurs, there's only the one way. So we get these 3 combinations that we then multiply together, and there's going to be 1,260 different combinations. And for this last example, we're taking what we had earlier of 9 players, but dividing them into groups of 3. So there's going to be 3 possibilities. Again, order's not critical. So it's 9 combinations of 3, 6 combinations of 3, 3 combinations of 3, and it would give you this. But as we read further, this is not correct, because they're saying that by having all the groups the same size, order is imposed on the groups. So they're saying what this would better be defined as is this formula, where the number of the ways 9 players can be divided into 3 groups would be all of this, and since repetitions are allowed, because the groups are in groups of 3 and not distinguishable, then we have to divide by 3 factorial, which is 6. So the correct answer is this one. Again, super challenging. You are unordering the sets by using 6 factorial. Okay, I give you some other things to think about in poker. I'm not a card player, so I don't know all of this. But if you're interested, you certainly can look it over. And we see some more of it here as we go on to some exercises. Now again, on your test, we'll only be including things that we do as part of your study plan and your homework. We're not going to pick out some wild, super complicated examples. And we'll wind this up.